You've seen the idea that you can add two vectors. Now we'll see what it means to add two vector spaces. This is called the direct sum. So let u and v be two vector spaces, and suppose that they share only the zero vector. We define the direct sum of u and v to be the set little u plus little v, where little u belongs to big U and little v belongs to big V. And it's written like this, u plus v. That is, u plus v is the set of all sums of a vector in big U plus a vector in big V. In Python, you could write the list like this. So here's an example. Let's start with vectors over GF2. We'll let big U be the span of these two vectors, and let big V be the span of this one vector. Now, note that every non-zero vector in big U has a 1 in the first or the second position, or both. And every non-zero vector in big V has a 1 in the third position. So there are no vectors in common other than the zero vector. So we can form the direct sum. And here's the direct sum. Taking the set of all vectors obtained by taking one vector from big U and one vector from big V. And carrying out these additions, this is the set. Now let's do an example with vectors over R. Define big U to be the vector space, the span of these two vectors, and define big V to be the null space of this matrix. Well, the vector 2, minus 2, minus 1, 2 is in big U. It can be written as a linear combination of these two vectors. In particular, it's this one minus this one. That same vector is also in big V, because if you multiply the matrix by that vector, you get the zero vector, which shows that this vector belongs to the null space of the matrix. There's a non-zero vector in both big U and big V. Therefore, we're not allowed to form the direct sum of U and V. Let's do another example of direct sum of vectors over the reals. We'll define big U to be the span of this set consisting only of this vector. You remember, the span of a set consisting of one vector is the line through the origin and the point represented by the vector. Similarly, let big V be the span of a set consisting of this vector. So this is also a line. Now, the only intersection of these two lines is at the origin. That is, big U and big V share only the zero vector. So we can form the direct sum. And what is the direct sum? It's the set of vectors little u plus little v, where little u is in big U and little v is in big V. So that's just span of the set consisting of these two vectors. And it's the plane that contains those two lines. Now let's use our knowledge of generators, basis, and dimension to better understand direct sums. So it's easy to show that the direct sum of U and V is a vector space. You just use the properties of vector spaces. Somewhat more interesting is to show that the union of a set of generators of big U and a set of generators of big V is a set of generators for the direct sum U plus V. So suppose U1 through UM are generators for big U, and V1 through Vn are generators for big V. Well, every vector in big U can be written as a linear combination of the vectors U1 through UM, because they're generators. Similarly, every vector in big V can be written as a linear combination of V1 through Vn, because they're generators. So every vector in U plus V can be written as a vector in U plus a vector in V. But what we've written is a linear combination of the vectors U1 through UM together with V1 through Vn. So that shows that those vectors span the direct sum U plus V. Now we're going to prove that the union of a basis for big U and a basis for big V is a basis for the direct sum U plus V. Well, a basis is a set of generators. So we already know from the previous lemma that the union of a basis for big U and a basis for big V is a set of generators for U plus V. So what remains to be shown is that the union is linearly independent. All right, so let U1 through UM be a basis for big U. Let V1 through Vn be a basis for big V. And we need to show that the union is linearly independent. Well, suppose that you can write the zero vector as a linear combination of all these vectors. By subtracting these vectors from both sides, we get this equation. Note that the left-hand side is a vector in big U because it's a linear combination of the basis vectors for big U. And the right-hand side is a vector in big V because it's a linear combination of the basis vectors for big V. So we've found a vector in big U that's equal to a vector in big V. Well, for the direct sum to even be defined, it needs to be the case that big U and big V share only the zero vector. So we've shown that this must be the zero vector and this must be the zero vector. That is, 0 is equal to this linear combination and 0 is equal to this linear combination. But U1 through UM form a basis. So the only way to get the zero vector as a linear combination is with the trivial linear combination. That is, alpha 1 through alpha m have to all be 0. And similarly, V1 through Vn form a basis. They're linearly independent. And so the only way to get the zero vector by taking a linear combination is if the linear combination is trivial. That is, if the coefficients are all 0. So that shows that all the coefficients here must be 0. That the only way to get 0 as a linear combination of U1 through UM together with V1 through Vn is with a trivial linear combination. And that shows that this whole set is linearly independent and therefore forms a basis for the direct sum. So we've shown that the union of a basis for big U and a basis for big V is a basis for the direct sum. An immediate corollary of this lemma is the dimension of U plus the dimension of V equals the dimension of the direct sum of U and V. The proof is that a basis for U together with a basis for V forms a basis for U plus V. If the direct sum of U and V is the space W, we say U and V are complementary subspaces of W. For example, suppose big U is a plane in R3. So in that case, any line through the origin that does not lie completely within this plane is a complementary subspace. Here's an example, and here's another example. This shows that there's potentially more than one complementary subspace. But let's show that there always exists at least one. We'll prove that for any finite dimensional vector space, big W, and any subspace, big U, there's another subspace, big V, such that U and V are complementary subspaces. We start with a basis for big U. Let's say U1 through UK form a basis for big U. Now, by the superset lemma, we can extend that basis to be a basis for big W by adding some vectors, let's say V1 through VR. Now let's define big V to be the span of these extra vectors V1 through VR. We want to show that V is a complementary subspace. That is, that the direct sum of U and V is W. There are two things to show. One, we have to show that U and V share only the zero vector. And second, we have to show that the set of vectors obtained by taking a vector in U and adding it to a vector in V is exactly the vector space W. Let's do the second one first. Now, any vector in W can be written as a linear combination of its basis vectors. Here we've written an arbitrary vector, little w in big W, as a linear combination of the basis vectors. Notice that this first part of the linear combination is a linear combination of the basis vectors of big U. And the second part of linear combination is a linear combination of the vectors spanning big V. This shows that this arbitrary vector little w in big W can be written as the sum of a vector in big U and a vector in big V. Now it remains to show that U and V share only the zero vector. Suppose some vector V lies in the span of U1 through UK, that is, it's in U, and also lies in the span of V1 through VR, that is, it's in V. So we write V as a linear combination of each of those vectors. That shows that these two linear combinations are equal. And moving these vectors to the other side, that shows that you can write the zero vector as this linear combination. But because these vectors U1 through UK together with V1 through VR form a basis for W, they're linearly independent. And so because you can write the zero vector as this linear combination, it must be that the coefficients are all zero. So that shows that this vector V must be the zero vector. So we've shown that the only vector in both U and V is the zero vector, so you can form the direct sum of U and V. And that completes the proof of the proposition.